Hello everyone, welcome back to another video. On today's video, I'm going to explain the Simulink model of single-phase bridge rectifier with resistive and RL load. And I aim to explain you. I'll try to cover the theoretical performance and compare with uh, the calculated values of a rectifier with the Simulink simulation. Firstly, to understand uh, this uh, single phase bridge rectifier, I'm going to show you a electrical circuit diagram of a full wave bridge rectifier. This rectifier is also called as full wave uncontrolled rectifier. Here we have an AC voltage source where and we are using 4 number of diodes. You know that in every voltage waveform, the AC source or AC voltage has a sinusoidal waveform, and it produces a positive and negative cycle of waveform. And this waveform during the positive half cycle from 0 to pi, this is a positive half cycle of the waveform, and pi to pi, it is a negative half cycle of a waveform, and it makes one period. So the single phase full wave rectifier uses 4 number of diodes: diode 1, diode 2, diode 3, and diode 4, and they are connected to the load, and V naught is a load. So during the positive half cycle of the voltage, the diode 1 and diode 2 is forward biased, and diode 4 and diode 3 is reverse biased. So during the positive half cycle, the current will start from the source and flow through the diode 1, then goes to the load, and it since the diode 2 is also forward biased, it will pass through the diode 2 and return to the source. This is the complete current path of in the positive half cycle. In the negative half cycle, diode 3 and diode 4 is forward biased, and diode 1 and diode 2 is reverse biased. Therefore, the current from the source will start from diode number 3, then it flows to the load and return back from a diode 4 and back to the source. That's why we can see at the output that the output voltage at the positive half, the current flows here. The blue one is the voltage, and the red one is the current. And in the negative half cycle, again the current flows. The voltage waveform at the load is something like this, and this waveform is called as a pulsating waveform, and the input AC is converted to a DC waveform. However, this is not purely a DC waveform, it is called as a pulsating waveform, and we are aiming to convert the AC input or AC power to a DC power. Now In the model, I am going to first calculate the values. You know that 415 is a line-to-line voltage in most of the country, and when I divide the line voltage from 415 divided by root 3, I'll get a phase voltage of 240 volt. This is a RMS voltage, and I'm going to assume my frequency at 50 Hertz. One of the important components that I have to measure is the VM. It's a peak voltage, and peak voltage is measured by VRMS times root 2, which gives you 330. This peak voltage will be same in the input and the output, and while we choose any diode for a rectifier, they have to always have 2 times of this peak uh, peak voltage, and it is also called as a peak inverse voltage. So uh, for my circuit, I have to choose a diode rating with the peak inverse voltage of approximately 660 volt. Now this is an next I'm calculating average DC voltage, which I will get at the output by using a formula 2 times peak voltage divided by pi, and I'm getting 216 volt. And load resistance, I'm going to use firstly I will use a purely resistive load, and then later change it to the RL load to show you some difference in the waveform. Then using the load resistance of 10 ohms, I can calculate the IDC, which is an average IDC, and I'm getting 21.6. And similarly, I can calculate the peak current of VM divided by R, which is 33.9. And after finding the VDC and IDC, I can find the output DC power, which is just a product. We have VDC times IDC, which will give you 4670 watts. And theoretically, when I calculated, I'm getting 214 to 216 VDC and 21 to 22 amps current and 4.6 kilowatt of DC output power. So this is what I am expecting after simulating my model. Now to explain the Simulink model, I have AC source, AC voltage source. This is a VM or peak voltage, which we got 339. I just round off and put it as a 340. The frequency is 50 Hertz, and other parameters such as 0. I have a current measurement block that will measure the current, and it is connected in a series. And I have a bridge, H bridge diodes. 4 number of diodes used: diode 1, diode 2, diode 3, and diode 4. And these diodes are connected to the load board and come back to the diagram. So connections of the circuit is similar to the circuit diagram we have found, and you can see that all the diode parameters will be same. Resistance of the diode 1 R1. R1 is when the diode is conducting, the resistance of the diode is 0.01 ohms, which is pretty low, and it says that the conductivity of a diode is pretty good, and inductance is 0. Then the diode's forward voltage is 0.8 and initial current 0, and I'm saying my snubber resistance and snubber capacitance of a diode are 500 and this one respectively. So what is the snubber resistance and snubber capacitance? These values determine how smooth the diode can switch on and off. So for switching the diode more smoothly, these parameters are used. Now at the top left hand side, I am measuring a power, an instantaneous power at the source. I am using a power block here where I will get an active power, which is an input power, or it is an AC input power in watt, and I'm getting a reactive power at the bottom. So similarly, at the load side, I am trying to measure a load voltage, the source voltage. So source voltage, to measure the source voltage, I'm using a voltage measurement block, which goes to the RMS block. The RMS block have the following parameters. The fundamental frequency is 50 and sample time 50 microseconds, and the display 1 will show you the VRMS or phase voltage of the source. Similarly, I am taking a current and given to the RMS block with the same parameters as earlier, and it will give me the IRMS value in in amps. And I am using a scope to see the current and voltage waveform at the source. Now I am using a 4.1 and 4.2 to this 4 gives the magnitude and the phase angle of a current and voltage, and I'm using a angle, the phase angle of a current and voltage and current, and I'm subtracting from voltage phase to current phase, and I gave it to the gain. So what I get here is a theta, and that theta is changed to radian, and I'm using a cos, a trigonometric function to get the power factor. Okay, as I said, I will first use the only a purely resistive load of 10 ohms to see how the resistive circuit or resistive load will impact the waveforms of the rectifier. Now at the load side, I have I'm giving I have another current measurement block which goes to the min with again the frequency 50 Hz and initial value input 0 and sample time 0, and this parameter is duplicated in exactly same in the another min 1 block. At the min here I'm getting IDC. Now I'm giving an AC input and I'm getting a DC output here. So IDC is a DC current, and again I have one more voltage measurement block that will measure the voltage at the load side, and this will measure the load voltage VDC, and it goes first to the main and we are getting a VDC, and this IDC and VDCs are given to the another scope to see how the rectified DC waveform looks like. And I am using a go-to block from IDC and VDC to find the power at the DC power or output power. uh, I'm just multiplying them and I'm getting a output DC power. Then I have used a go-to block at the input AC power, and by dividing the output by input I'm getting efficiency, and by multiplying with gain of 100 I'm getting an efficiency in percentage. Okay, and one more thing, I'm using a power give from the Simscape, then changed my solver to discrete and sample time this much and apply OK. And I'm going to change some values in the model setting, and I'm going to keep my starting time 0, then stop time 1, then change the solver selection type to fixed type, then again fixed step size will be this much value, and apply. Yep. That is the single phase bridge rectifier model in Simulink. And let's run the simulation, right, and see how the model works. Okay. We have a phase voltage of 240 at the source, and if you calculate, I didn't calculate the IRMS, but if you calculate the IRMS, you will get 23, which is exactly same as the calculated value, and this simulation value is exactly same. I'm getting a power of AC power of 5745 watt at the source, and I'm getting a power factor of 0.75. which is approximately 0.8. Then I have reactive power, but that is not really important for now. We really do not need reactive power. Now at the load side, what we are getting is a DC voltage and current and power. And okay, before going to the load side, I will show you the AC waveform at the input. Yep. Okay, what you can see here is the sinusoidal waveform of a AC sinusoidal waveform. Yellow is a voltage waveform, and blue is a current waveform. And we have calculated, or we found that our peak waveform is 340. So yes, it is 340 here. Voltage, peak voltage is 340 and negative 340 at the second half. And the current, and let's check, we have an average voltage of 200 something or 100 something. It should be somewhere middle. This will be 170 to something, should be an average voltage, AC voltage. Okay, anyways, I will show you. Firstly, the current measurement. In the current measurement, the peak voltage is 25, and and mhm, the peak current is 33 amps. It's not 33 amps. Wait. The peak is 67 amps. No. It's 30. Sorry, it's 33. Yep, this is the one. 33, and the average AC voltage is around 6.7 amps, and RMS voltage is 24, as shown in this RMS voltage. This is a AC waveform. Now at the load side, you can see that we are getting around IDC of 21.48 amps, which is almost similar to the calculated average DC current, and DC voltage is 214. So our DC voltage is 416. Yep, the rectifier has rectified the AC voltage, and now our DC output power is 4614, which is lesser than the PAC as expected. And after finding the efficiency, we are getting an efficiency of 80.33, which is an perfect efficiency, or the perfect ideal in the ideal cases. For the single phase bridge rectifier, the efficiency of a single phase bridge rectifier is 81, so we are getting almost 80.33, and the simulation is working perfectly. Now let's see the waveforms. Okay, this is our waveform, and Make legend. Okay, I already have a legend. Now the blue one is a voltage waveform, VDC, or DC voltage waveform, and the yellow one is a current waveform, and its peak is approximately 330. Yep, 338. So anyways, let's search from here. Yep. For the voltage, we are getting a peak of 338. It's 340. So look, why we have to why we need the we need to consider the peak inverse voltage of a diode, because we have to resist twice of this current, this voltage, and the average VDC is 214. Somewhere here. Yep, that's the voltage form. I don't need voltage waveform. Now let's see how the current waveform looks. Okay, you can see that we have a 0 here, and at the negative side there is no more a sinusoidal waveform. Both the current and voltage waveform, there is no more waveforms in the negative cycle. So we have already rectified the sinusoidal waveform into a DC waveform, or it is called as a pulsating waveform. And in case of a current, you can see that the peak current is the peak is 33.833, and mean peak IDC is 21.4. That's almost here. So there's a mean, there's a peak, and we're getting a DC waveform or pulsating DC waveform. And the rectifier has rectified the circuit. Yep. What we can conclude from this this circuit, it says that the rectifier has done its job. It has converted the AC waveform to a DC, or it has converted this AC power to a DC power, and with only a resistor or a purely resistive load, both the voltage and current are perfectly in phase, and even the efficiency is nearly ideal, and with only small losses from the diode drops, right? It's not exactly 81. So, and we can see that the output waveform is not really a perfect DC waveform, and this is a pulsating waveform, and there is a ripple in the waveform, but we can reduce this ripple using the capacitor, or this capacitor will work as a filter, which will be connected somewhere here parallel to the load, and it should reduce the waveform, and it should filter the waveform and give us a resultant waveform more like a DC waveform. Yep. And I want to show you one more thing. I will change the load to RL load, which is normally the domestic, industrial, or commercial load are usually a RL load, and I'm uh, keeping my inductance of this value. And let's simulate once more and see how the waveform changes. Okay. uh, Now let's see. Okay, we want the voltage too. Now you can see that due to the inductive, the voltage waveform has remained same. No, uh, it has remained same like a purely resistive load. However, the current in the RL load circuit is different, and it is still a pulsating waveform, however, but it at the start it increases from 0 to some value of current, like here it's almost around 21 or something, and it's taking some period of time to increase the current at the start, and then stabilize itself at a certain period of time, for us at a certain value of current. So that is the difference between the purely resistive circuit and uh, purely and RL uh, load circuit. Okay, that's all for today. Thank you for watching. We'll see you in the next video.